Good morning everybody. Today I shall be discussing about feedback amplifiers. We discussed about feedback in the context of biasing, transistor biasing. We applied a voltage which is proportional to the output current at the input in the negative direction, and in the process we achieved bias stability. That means if there is a tendency to increase in the bias current, increase the bias current, that is the collector current, then a voltage which is proportional to the collector current appears at the input in the opposite direction, and the base to emitter potential is reduced, and in turn the collector current is controlled. So in the context of bias stability, we discussed about feedback. The same feedback concept can be applied for when we talk about the small signals or the alternating signals also. So in turn we get some advantages if the bias is negative, if the feedback is negative. So negative feedback gives rise to the following advantages. So the advantages are, so number one, stabilized voltage gain, stabilized voltage or voltage and current gains. Then we have higher input impedance than the input impedance without feedback. Then we get improved frequency response, if there is any frequency distortion, it gets reduced. Then lower output impedance compared to the amplifier without feedback. And we have reduced noise in the output and more linear operation. A transistor is a nonlinear device, and for small signals it acts like a linear device. But please note that if even for the small signals also, if you really examine it, it's a nonlinear characteristics. The only disadvantage being, the only consideration being the nonlinearity is very small. However, in certain applications that nonlinearity matters, and if you want to improve the linearity, we can improve the linearity by using the feedback concept or feedback in the amplifier circuit. Now we shall discuss about what is feedback in detail, and then how many types of feedbacks are possible and so on. So let us consider an amplifier with gain equal to A. It has an input and it has an output. This is a typical symbol for an amplifier, and let me indicate the input voltage as Vi with respect to the ground. And in a feedback amplifier, what we do is we take the output signal whose output value is V0, output voltage is V0, and we take a fraction of that, that means a fraction of V0, that means beta times V0, is fed back to the input. Usually in the opposite polarity. So this is the feedback amplifier with the input here and output here, and this is the amplifier without feedback. So it takes an input signal Vi and gives an output signal V0. Now to this amplifier, or from this amplifier's output, we are taking a fraction of that, that means beta times V0, and that voltage is say Vf, and that voltage is made to subtract from the input signal, and then the error signal is fed to the amplifier, or the difference is fed to the amplifier. Now the input voltage is Vs, say the input voltage is Vs, in which case Vi is equal to Vs minus Vf, and Vf in turn is beta times V0, and V0 is A times Vi, therefore the ratio between V0 to Vs, that is the overall gain of the feedback amplifier, because this is the feedback amplifier now. So this is the feedback amplifier, and this is the amplifier without feedback. Now the gain of the feedback amplifier now, that is the ratio between output and input V0 by Vs. So this is, let me indicate this as AVF, F indicates the feedback amplifier. So that is equal to V0 by Vs, and we have V0 by Vi ratio so we have here Vs to Vi ratio, and V0 by Vi ratio is A. Therefore, the overall gain of the amplifier is 1 by 1 plus A beta, according to this expression. Please note that Vi is Vs minus A beta Vi. That means Vs is equal to 1 plus A beta into Vi, Vs is, and V0 when expressed in terms of Vi, V0 is A times Vi. Therefore, V0 by Vs ratio is A by 1 plus A beta, where A is the gain of the amplifier without feedback, and beta is the ratio and the voltage ratio, or output to the feedback to output quantity ratio, of the feedback to the output quantities, and in terms of this, the gain of the amplifier is like this, where the feedback is negative. If the feedback is positive, you would have got this as A by 1 minus A beta. Now as an example, if A is equal to 100, or okay, let me take A as 1000 and beta as 0.01, you will get an AVF of 1000 by 11, which is approximately equal to 1 by beta. When A beta is much greater than 1, so this is approximately equal to 1 by beta, when A beta is much greater than 1. So please note that now the gain of the feedback amplifier is approximately equal to 1 by beta. and it is becoming independent of A, the transistor amplifier gain. So this is how stability can be achieved. We shall discuss about it in detail in the subsequently, but please note that with feedback this is the expression for the gain of the amplifier. Now if the feedback is positive, then the gain would have been, in this particular example, and the gain would have been A by 1 minus A beta, and in this particular example it would have been minus so minus 1000 by 9. And if A beta is made to be of the order of 0.5, it would have been A by 1 minus 0.5, it would have been A by 0.5, and the gain would have been 2000. And if it is 0.9, A beta is 0.9, gain would have been 1000 by 1 minus 0.9, it would have been 10,000. Like this, with proper positive feedback, you can increase the gain of the amplifier. But that's not an advantageous thing, because in the process the amplifier becomes more unstable, and amplification is not a problem. If you want amplification, high amplification, you can cascade such amplifiers and you can get a gain of, with two such amplifiers the gain would be A square, and getting gain is not a problem, but stable operation is more important. Therefore, we always use the feedback concept for negative feedback only, except in the case of oscillators. So this is about a feedback amplifier and the gain in the case of a feedback amplifier. So now the question is, how many types of feedbacks are possible? Please note that we have different kinds of amplifiers. We have voltage amplifiers, current amplifiers, transconductance and transimpedance amplifiers. That means the input and output signals of interest are of different types. Input signal can be voltage or current, and output signal can be a voltage signal or a current signal. So naturally, when you apply feedback, the feedback will be from, the feedback is from an output voltage or output current, and the feedback quantity is again an input current or input voltage. So in the context of these, there are different connections possible. So types of feedback connections. So in an amplifier, the output can be an voltage signal. If the output is an voltage signal, we sense the output. So that means while sensing, so we tap the output parallelly. So we tap the output voltage means you tap the output parallelly. So this is known as voltage feedback. And the voltage feedback can be applied to the input in shunt or in series. So it is applied in series through a network, a feedback network. We get a feedback signal, and if it is a voltage signal, we apply it in the negative direction to the input. so that the source voltage is now the feedback voltage Vf is applied in the opposite direction to the source voltage, and it subtracts. Now the effective signal at the input Vi is Vs minus this feedback voltage Vf, and beta is naturally in this case Vf by V naught. It is the ratio between the feedback voltage to the output voltage. So this is the amplifier without feedback, and the amplifier gain is V naught by Vi. I repeat, this is the amplifier without feedback, and its output to input voltage ratio for the I am talking about the amplifier. For the amplifier, the output to input voltage ratio is the gain of the amplifier without feedback, that is V naught by Vi. Now the feedback voltage is Vf, and Vf by V naught is the feedback factor beta, and that is also voltage, and this voltage is applied in the opposite direction to the input, and Vs minus Vf is equal to Vi. So this is the situation in an voltage amplifier. If the amplifier under consideration is a voltage amplifier, the output signal is a voltage signal and input signal is a voltage signal. Therefore, we tap the output voltage and apply it to the input voltage in the opposite direction. So this is typically done for voltage amplifiers. And this kind of connection is known as voltage series feedback, because the tapped signal is the voltage signal and the feedback is applied in series. Therefore, it is known as voltage series feedback, which is applicable for voltage amplifiers. And in this case, gain of the amplifier can be shown to be A by 1 plus A beta, using the same expression we applied previously. So A by 1 plus A beta. In fact, here we have considered the voltage amplifier. That's why this is Vf, this is V naught, this is Vi, Vs, and we got the expression. So the same expression is valid here. Therefore, gain of the amplifier is A by 1 plus A beta. And the type of feedback is voltage series feedback. On the other hand, when the input is a input signal is a current and the input source is a current source, naturally we apply a feedback, and the feedback signal, when we apply feedback, we see that the feedback signal is current, and this current is in the opposite direction to the driving. So that is true in the case of a trans impedance amplifier, where the input signal is current and output signal is voltage. Therefore, in a trans impedance amplifier, we have this kind of scenario. This is an output, this is the output signal V naught, and A is equal to V naught by II, where the input signal is current signal II, and the output, that is the voltage, is tapped, and through a feedback network a proportionate amount of current is generated from the output voltage, and this current is connected to the input in the opposite direction. This is the input current source, and from the input current source some current is forcibly drawn from the source into the feedback network. Therefore, you are not adding any current to the source current, but then you are drawing current away from the source. So, how much of it is drawn? An IF amount of it is drawn, and this IF is beta times the output signal V naught. So, in this case now the type of feedback connection is the voltage shunt feedback connection, which is applicable in the case of a trans impedance amplifier. This is applicable in the case of a transimpedance amplifier. Now, let us obtain an expression for the gain in this amplifier. So, the gain without feedback is V naught by II, which has units of impedance, and the gain without feedback is AF. So, which is the ratio between V naught and IS, and naturally it will have units of ohms. It is a transimpedance amplifier. Now, II is equal to IS minus IF, and IF is beta V naught, and V naught is A times II. Therefore, beta into A into II. Therefore, the ratio between II and IS, or IS to II ratio, is equal to 1 by 1 plus A beta. For V naught to IS ratio is, so V naught by II ratio divided by IS, therefore AF is equal to A by 1 plus A beta. Now, IS by II is right, that's right. There is a mistake here. IS by II is 1 plus A beta. Now, AF is V naught by IS, therefore V naught divided by IS is equal to V naught by II divided by IS by II, therefore that is equal to A by 1 plus A beta. Therefore, V naught by, since V naught by II is A, hence this is the expression for the gain in the case of a feedback amplifier. Now, this transimpedance with feedback is smaller than the transimpedance without feedback, and when A beta is much larger than 1, the gain or transimpedance AF is equal to 1 by beta. It is again becoming independent of the amplifier parameter A, and it is totally becoming a function of the feedback network itself. Please note that the feedback network is usually a passive network, and in the example which I have given here, it is a ratio of 0.01. That means it is a voltage dividing ratio, so which can be obtained with the help of two resistances. If this is the input applied here, and if this is the feedback output that is taken, so please note that Vf to V0 ratio, that is beta, is equal to R2 by R1 plus R2. So this ratio can be obtained with the help of simple passive elements like resistances, and these are not active elements. Therefore, this ratio, this network is a stable network, and this network, the amplifier involves active elements. Therefore, it is not stable, because different amplifiers with different transistors exhibit different amount of gains. The HFE may be 100 in one transistor. With the same transistor, the HFE, another, if you pick up another transistor, it may exhibit a HFE of 50. So HFE directly gives you, or beta directly gives you the current gain. So here itself there is a difference in the current gain. Therefore, different amplifiers may exhibit different amount of gains, and then in the process of feedback, you are making it independent of the amplifier parameters, and it is, you are making it a function of the more stable feedback network parameters. Well, if you don't use the amplifier and use only the feedback network, you cannot get any amplification, you will get only a ratio. So that is meaningless, therefore. So this is a voltage shunt feedback connection, which is applicable in the case of transimpedance amplifiers. Well, so far we discussed about voltage feedback. Now let us see how we can use current feedback. In a current feedback network, we tap the output signal, output current, and to tap the current, you have to cut the line and sample the current and make the current, output current, pass through a feedback network. So if this is I0 equal to the load current flowing into the load, then the same I0 is made to pass through the feedback network. Now, if the input signal is a voltage signal, then naturally we try to get a feedback signal as a voltage signal, and we apply this signal in the negative direction to the input, and the resultant signal is fed to the input. The subtracted version of the signal is. So this amplifier is a transconductance amplifier, and its gain therefore is a ratio between output current and input voltage Vi, which has units of mhos. And the feedback is, on the other hand, the feedback element produces a voltage signal at its output and takes the output current at the input. Therefore, the feedback network has units of impedance, and beta here is naturally Vf by I0. So now this is the feedback amplifier, and it is current feedback, and here we are applying feedback in series. Therefore, it is known as current series feedback. This is applicable in the case of amplifiers, transconductance amplifiers. Now, it can be shown that the gain of the amplifier is again A by 1 plus A beta. It can be very easily shown. So Vi is here also, Vi is Vs minus Vf. So that means Vs minus beta into I naught, and I naught to Vi ratio is A, therefore this is A beta into Vi itself. So output current I naught to Vi ratio is A, Vf is beta times I naught and multiplied by A times Vi. So it is A beta times Vi is Vf, and Vs minus Vf is Vi. Therefore, the ratio between Vi and Vs, Vs by Vi is equal to 1 plus A beta, and I naught to Vi ratio is A. Therefore, AF is equal to A by 1 plus A beta, where AF is the ratio between I naught and Vs, which has units of conductance. Now, if the input signal is also a current signal, that means in the case of a current amplifier, we apply a current in the opposite direction to the input current from the current source. Then the connection can be like this. This is the amplifier with input signal as a current source, applied to the amplifier, and the output signal is a current signal I naught. Now we make the current pass through the feedback network to obtain a current which is proportional to the output current I naught as the feedback current. And apply this current in the opposite direction to the input. So that means we force some current to go out of Is into the feedback network, and this current is proportional to the output current. And since this is a current amplifier, its gain is I naught to Ii, so where this is Ii. So this type of connection is known as current shunt feedback, because the feedback connection is shunt, and the output quantity that is sensed is the output current. Therefore, it is current shunt feedback, so which is typically applicable in the case of current amplifiers. In this case, you will get the gain of the amplifier with feedback as the ratio between I naught and Is, and similar to what we have obtained. So you will get the expression for the gain as A by 1 plus A beta in this case also. Therefore, this is the gain of the feedback amplifier. So, these are the 4 different connections possible depending on the input and output signals being current or voltage. Any questions so far? Questions?
Is it possible to get 2 types of gains, having current gain and voltage gain together for a single amplifier using 2 feedback networks?
Your classmate's question is it possible to have voltage gain as well as current gain with 2 different networks? So, please note that you have the output signal can be converted from a current signal to a voltage signal through a resistive load. So, you can convert an output signal from a current signal to a voltage signal, but please note that both are proportional, and the current gain and voltage gain are dependent to each other through the relationship Ri and RL, through RL and Ri, and as long as RL and Ri ratio remains the same, you have the current gain and voltage gain ratio remaining the same. Therefore, whatever is the effect of feedback on one, that is the voltage gain, you will have the same effect on the current gain also once the feedback network is the same. If the feedback network is different, naturally you will have a different outcome. Any other question? Now, let us see what is the effect of feedback on input impedance. So, input impedance with feedback. So, let us consider the case of a voltage series feedback circuit and discuss about the input impedance, because the input impedance has depending on the connection, the input impedance has 2 types of variations. With voltage series feedback like this, when the feedback is negative and applied in series, the input impedance increases, and in a connection like this, the input impedance decreases, because for the same voltage applied, if you apply 1 volt here and because of feedback the voltage is that is applied here is say 0.5 volts. What is the net voltage applied to the amplifier? It is 1 minus 0.5, it is 0.5 volts. And if the resistance, input resistance of the amplifier is 1 kilo ohm, how much current does it draw? 0.5 volts divided by 500 ohms. Now the same current flows from out of the source. So here 0.5 volts divided by that current is 500 ohms. Now it is 1 volt divided by the same current. So with respect to the voltage, the current that is drawn is half that of this one. Therefore, the input impedance is effectively increasing. Say whatever is the current that is being drawn for 0.5 volts, okay, will be now drawn from a 1 volt source. 1 volt divided by that current and 0.5 volts divided by this current. 0.5 volts divided by this current is Ri. So 1 volt divided by this current is going to be 2 Ri. So Ri is effectively increasing in this connection. It's getting doubled in this particular example. I repeat, because of some voltage reduction here, with that reduced voltage, the current that is drawn would naturally be lower from the source point of view. Okay. Because of that reason, the input impedance increases in this particular case. Therefore, there is an increase in the input impedance in this series connection. On the other hand, in the shunt connection, you will find that the input impedance goes down. Input impedance decreases in the shunt connection, because if the current drawn is II, and now the current drawn from the source here is more than this. So for a particular voltage here, the current drawn is more. So that's what happens when a low resistance is connected. When a low resistance is connected, current drawn is more from a voltage source I am talking about. Therefore, the input impedance effectively goes down in the case of a shunt connection. So let us now see analytically how the input impedance is going down. Now the current drawn here is, if this is Ri for the amplifier, if this is Ri, that means Vi to II ratio is Ri. Vi divided by II is equal to Ri. Now what is the input impedance here? It is RIF. Now same II is going from a source of Vs volts. So RIF is Vs by II. And Vs is definitely larger than Vi, and the difference is Vf. So Vs by Vi ratio is obtained as how much? 1 plus beta times, Vs is 1 plus beta times Vi. That's what we obtained earlier. 1 plus A beta times Vi. Therefore, this is equal to 1 plus A beta times Ri. RIF is 1 plus A beta times Ri. In the example of A equal to 1000 and beta equal to 0.01, so we have this as 11. So RIF is 11 times Ri in that particular example. So this is approximately A beta times Ri when A beta is much greater than 1. So quantitatively, this is the expression for the input impedance with feedback. We shall discuss about it in the next class.